Second, as we are going to live stream. All right. Thank you for joining me, everyone. Today we are joined by Johannes Noller from the University of Portsmouth. Before this, he was an Ernest Lund Fellow at the University of Cambridge, and prior to that, he was a junior fellow in Zurich. And today we'll be talking to us about testing gravity on all scales. Do you want to take it away?
Sure. Thanks a lot, everyone, not just for inviting me, but especially for being here in person. Like I told many of you, I think it's the first in-person seminar I've done for about 2 years. So I'm, no matter how much you'll enjoy this, I'm going to have a hell of a time. So, so that's going to be great. Like Rachel was saying, you've seen I've gone for a suitably megalomaniac title, which of course I'll fail to live up to. But hopefully, what I will manage to do is have a little bit of a whistle-stop tour for you, where we talk about all kinds of different systems, I guess in a very broad sense, theoretical constraints. You can think about actual physical experiments and so on that live on different scales, different energy scales, and which all test gravity in one way or another. I think it's the second caveat I should really tell you about is that a lot of the things I will tell you about are applicable to all kinds of gravitational physics, but mostly I'll focus on things that are related to dark energy as a concrete application. So if there's any particular point where you want me to flag out whether this is more dark energy specific or more widely applicable, then do just stop me. But most of the examples I'll go through are dark energy related. Very good. And so, I hope you still have the mind power for 1 more hour of testing gravity. I know the people here were just in the Journal Club and heard 1 hour about this as well. So thank you for your endurance in advance, I guess. Good. So let's get started straight away. This is the plot of the talk, a bit boring for now. But it's basically just a single line plot, as you can see. That is some measure of scale in our favorite units. So let's start at the top with some measure of energy scale, really frequency here, which goes all the way from around 10 to the minus 20 hertz here to something ridiculously large like 10 to the 43 hertz. And as good physicists, we can change our favorite units here, right? So we can equivalently talk about this in terms of distance scales. So 10 to the 23 kilometers all the way to something like 10 to the minus 38 kilometers. And if you want, and we'll do this later on, you can also turn this into an explicit energy scale, again, your favorite units in electron volts or something like this. So we're going to start populating this here with different systems, and then we'll cherry pick a few to talk about. So number one, all the way on the left, we have where cosmology is at home. So the largest scales we observe in the universe live at around 10 to the minus 18 hertz in those units, or they probe distance scales of around 10 to the 23 kilometers or so. As we go to slightly smaller scales here, and similarly slightly larger frequencies, we start resolving some of the structure in the universe. So that's where large-scale structure tests live, where you start resolving things like clusters of galaxies, still all in linear regime. And then, of course, as you go further to the right, you start going more and more into the nonlinearities of cosmology. Going further to the right, this is more where gravitational wave science lives. So here we're talking about frequencies order 10 to the minus 7, 10 to the minus 6 hertz. That's the kind of frequencies where you see supermassive binary black hole mergers. The Hulse-Taylor binary starts sitting a little bit further to the right. And then all the way here at around 10 to the 2 hertz, or scales of around 1,000 kilometers or so. That's the kind of energy scales that LIGO measures at the moment. Somewhere in between are some of the, I guess, classic gravitational tests like orbits of planets or the Moon-Earth system. And then all the way to the right is where things get really messy. And this is, I guess, some level, this is going to be where you start talking about quantum gravity, some kind of UV completion of physics in general, but in this context, especially gravitational physics. Good. So what I guess want to do in this talk is really get 2 messages across. Message number 1 is there's a lot of complementary constraints that we can get from lots of these different systems together. So there's a bit of a gold mine in terms of combining constraints which test this physics in different ways. that hopefully by putting them together, we can get a sort of a better synoptic understanding of gravity at large and dark energy specifically here. So that's the full-on positive message. The second message is much more one of caution, which is that you need to be quite careful when you start putting these different constraints together. Sometimes they're real theoretical obstacles in terms of you just not being able to do it. Sometimes it's just a case of it being tricky and you needing to be careful. And some of these things are surprisingly subtle, and so you need to be very careful when you do put these different constraints together. So that's if this is all you have time for, you can take that message away, and I'll just go through a few different systems now and hopefully convince you that there's something interesting in all of them. I was going to make this multiple choice and get you to choose which three systems you would like to hear about, but that was much more of a nightmare to prepare for. So instead, you'll get zero choice at all, and I have prepared the bits. So do feel free to complain to me afterwards if you feel I picked the wrong systems, but we'll see how that goes. Okay, this is not the first system I want to talk about. This is my way of trying to jazz up the introduction a little bit. So I'm going to use GW17817, the neutron star binding merger, as a way to hopefully lay down some of the basic concepts in a way that's a little bit more interesting than just writing down all the basic equations. So most of you will have seen this plot a lot, right? This is, I guess, one of the really nice manifestations of why this is such a beautiful event, where all the way at the top left here, we see the signal observed by LIGO Virgo from this neutron star merger. You can see this beautiful line as the in-spiral happens, and these two neutron stars get closer and closer together. And then you can see all kinds of optical follow-up events that also detect the same system. There's many interesting things about the system. One of the most interesting is that you really get this race between light and the gravitational wave signal going over a fairly long distance, 40 megaparsecs or so. And so you have this amazing dual timer, right, where you can measure the speed of gravitational waves amongst other things as well. So rather than just noodling on about this constraint, I just wanted to use this example to think a little bit about why this is such a good test of the speed. And the sort of rationale behind that is going to come back to us in lots of the other different examples. And this is a little bit related to a question I think that Phil was asking earlier on in the journal club as well. So why is something like this test actually useful for testing new gravitational physics as opposed to just telling us about the speed of gravitational waves? And the reason is kind of two-edged. Edge number one is that if I put on my particle theorist hat, GR is extremely special. If you try to write down a theoretically consistent theory for a single massless spin-2 particle, that's what GR is built of, there's only going to be one answer that you can come up with. You can be cruel and say this is a PhD project, and your student will fail continuously to come up with something new. And then in the end, you will find that actually there's some deep underlying reasons, Lorentz symmetries and so on, that GR comes out of this as a unique answer. Now, what's the corollary of this statement? The corollary is that if there is some interesting new physics coming in, generically this comes with some kind of new variable, some new dynamical degree of freedom that may be hidden, right? It may be that you give the graviton a mass and there's some extra new polarization. It may be explicit. Someone really tells you there's an extra scalar field, there's an extra vector field, something like this. But there's going to be some new kind of dynamic, some new variable, some new degree of freedom there. So very generic. Now put yourself into the sort of the pilot of the gravitational wave as it's going from this event to us. What it will see is the soup of stuff that it's going through, right? It experiences the universe as some kind of medium that it's going through. If there is some new particle, some new element in the soup, right, there's going to be some background configuration for this new soupy element. And so what that really means is that this can change, and hence the picture, the effective refractive index of this overall medium that the gravitational wave is going through. So this is, like we discussed early on, right, all to do with spontaneous breaking of Lorentz symmetry and so on. So this doesn't need to happen, but something that in a lot of cases where this extra degree of freedom is there, it'll change the medium in such a way that it changes the refractive index. And so this is precisely how people used optics in like the 17th and 18th century, right? You have a new lump of stuff, you shine light through it, and you use that to learn about the properties of the stuff, right? Your light is like the probe that shines through the medium and it tells you about the medium. This is the exact same thing we're doing with GW17 or 817. We're shining a gravitational wave through the universe. And so from its speed, we learn something about the medium, and so potentially about the presence of new degrees of freedom. Okay. So one quick example, which I never know whether to show or not. To some of you, this will look horrible. Some of you, this is your bread and butter. This is one standard set of scalar tensor theories. Lots of you will recognize this as a Horndeski class. If it's not something that you play with all the time, a good sort of 0th order approximation is to think of this as the most general thing you can write down, which has a new scalar degree of freedom, where the new physics is in a scalar. Those of you who know about this will know about the loopholes in the statement I'm making, but I'll leave it at that. And so this is some big thing here, right, where you say, well, let's assume we write on something fairly general where this new degree of freedom, this new physics, is encapsulated by an extra scalar. And there's lots of freedom in this, right? There's all these red guys here, the G2, G3, G4, G5, which are really functions of the scalar and its first derivative, where this combination here. And there's all sorts of derivative combinations, right, where the metric heights and the Christoffel symbols and the Ricci scalar and so on. There's a tensor and there's a scalar. So now someone gives you your favorite theory. Let's say it's this one, maybe it's another one. You can work out what the speed of gravitational waves will be, right, in this new medium provided by this thing here. And when you do that for this monstrosity, you find that everything in blue generically gives some order 1 effect on the speed of gravitational waves. So if you just take some measurement at face value, like from GW17 or 817, that tells you you're damn sure that to an extremely high accuracy, 1 part in 10 to 15, the speed of gravitational waves is the speed of light. And then you can say, well, to all intents and purposes, certainly for anything that we look at in cosmology, all this blue stuff here is super subdominant because it would generically affect the speed of gravitational waves. And you're just left with this tiny little bit here, and more specifically, something that looks like that here. I'm not really, for the purposes of this talk here, I don't really care about the specific form of this. This is just some sort of sleight of hand way of trying to give you a slightly more concrete way of quantifying that this is actually a useful text. Very good. Okay, so now let's put two things together. And what I will do for now, and probably some of you are already sort of second guessing what I'm doing, is I will tell you what I think is a sort of textbook-like vanilla story, which is a very linear story, where I'll put together more and more of these constraints. And we are all happy and living in this sort of utopian land where they all just line up together and the constraints shrink more and more and more, and we learn more and more about gravity. And then I will get this sort of house of cards to fall in hopefully the second part of the talk, where I sort of will go through some of the caveats, which I will argue are much more than just caveats. They really kind of tell you that you shouldn't have done this the way I'm doing this now. So everything I'll do now is wrong, but you will still have to sit through this for 15 minutes. So let's start by taking this constraint as I just gave it to you now. Again, for the purposes of being concrete, I'll just assume that we are in this universe where there's some new scalars, some new physics. I have this wonderful constraint that knocked out all these interactions a second ago. Now let's go to the other side here, just to standard large-scale linear cosmology and see what extra constraints we can put on this as well. Okay, so question number one, right? We want to learn about the new physics. We want to learn about dark energy and so on. What I'm saying here is, what are the axes, right? And what I really mean is, of course, there's a very nice and unique way to BGR, right? If I now say I want to probe what the new physics could be, how dark energy could be different, in principle, you may say, well, that's a little bit of an ill-defined question here, right? Surely there's a plethora of different ways how this could be different. How do you figure out what the right parameters are to measure this? And so it turns out that this is a little bit better defined than what you may have feared, in the following sense. So it's true that in principle, right, if you try to dream up any kind of new interaction, new way this new degree of freedom is talking to matter, to the graviton, things like this, you may come up with lots and lots of things. But there is lots of theoretical constraints as well, right? You can't just dream up anything. If you want something that in principle is Lorentz invariant, if you want something that doesn't have any horrible instabilities that make the universe explode, all of these things place constraints on what kind of theory you can write down. And so what I'm just sketching extremely briefly here is, imagine, like in the previous example, we have some covariant theory like this Horndeski theory in the first place. when I now do linear cosmology, what I'm really wanting to learn about is very small scale fluctuations on large scales of the universe, like from the CMB or in large scale structure. They are determined by this thing down here, which is really the same theory, the same action, but perturbed up to quadratic order. So up to quadratic order in these little perturbations. So I'm expanding, and this is far too small, one of the classic fallacies of giving a talk, right? I'm expanding my metric in terms of some background metric and some perturbation, which ignoring the indices is this gamma, and I'm expanding the scalar field in terms of some background and some perturbation, which is this delta phi. So you find all the quadratic combinations of this thing, expand it around some cosmological background, because that's what we're doing in this example here, working with cosmology. And you will find that actually all the information about the intricate structure of your underlying theory combines just into a few parameters. And these are these famous alpha I parameters, which were really first found by Emilio Bellini here and Elisa Vicky. And so these are these red guys here. If you want to think of this in terms of the I guess the language, for example, Tim was using earlier on, these are really the coupling constants of your theory around this particular background that tell you about the strength of these different types of interactions. Just that this is more complicated than in standard particle physics, because in standard particle physics, you work on a flat, boring Minkowski background, so all the coupling constants are just constants. Here, these, as I would call them, Wilson coefficients, are not just constants, they are functions of time, because your background is changing in time. Cosmological backgrounds are expanding, so there's a time dependence. So, there's a handful, depending on how you count, somewhere between 3 and 5, different free functions, which are sort of the axes in which things can be different if there's this new state. So let's focus on just 2 of them, just because otherwise it would be some ugly triangle plot. And we're just zooming in on something there. Phil is smiling because he knows my grief with triangle plots. And we're focusing on 2 parameters. One parameter here is basically telling you what our cosmological measurement tells you about the gravitational constant G, about Newton's constant. We have amazingly tight constraints from pendulum experiments and so on Earth. Imagine you don't know about those. Now you do your cosmological measurement that will tell you something about the strength of gravity there. The other parameter is telling you about how strongly this new scalar physics that we're working with here as a fiducial example is coupling to and interacting with the standard graviton, the gravitational perturbation of your tensor, of your spin 2. And there's technical names that lots of you guys know, right? This is telling you about the kinetic braiding. This is telling you about the running of the effective Planck mass. But some of you will know. For the others, I guess you know that these are 2 parameters that somehow tell you something about the interaction strengths. Good. Maybe I should say very, very quickly, what I'm really doing here is, remember a slide ago, I was telling you about these coupling constants, which were not really constants, but functions of time. So really what I'm plotting here is some kind of ansatz where I'm assuming that these functions can be captured by a single parameter, and they are just proportional to the energy density of dark energy. This is a sort of brute force phenomenological fit. This is specific to the dark energy case, where I'm basically saying, well, as a first order ansatz, if this has something to do with dark energy, I want it to switch off when dark energy is not important, but when dark energy is important, this thing comes into the game. So I think you should think of this not as a particularly fundamentally motivated ansatz, but some sort of first brute force attempt. And so I'm just plotting, these axes are not a function of time, because that would be ill-defined, but just this overall constant coefficient. There's much more clever thoughts about how you can improve this, including this paper I'm advertising somewhere at the bottom here, which you probably can't read, but they're happy to talk about it later on. Good. So final thing about this plot is these parameters are chosen such that GR and some other theories live at the 0,0 point. And so if you move around in this plot here, then you are in some other theory, in this case, with a new scalar degree of freedom. So if in some future scenario you get an ellipse that lives up here, for example, then this is a way of testing. Well, this is a way of, in that case, seeing that there's some new physics, which is not just lambda CDM or GR. Unsurprisingly, we'll see that current data doesn't tell you that, but that's the underlying principle. Okay, now, how am I doing? Too slow as usual. Okay, I'm just going to put 2 types of constraints here. And what I'm really doing here is lumping lots of cosmological data constraints on this here. The yellow contours are, to all intents and purposes, just Planck constraints. So all the standard Planck likelihoods, I guess you can find, lensing, temperature correlations, polarization, and so on, and plotting constraints onto this space here, where I'm assuming that the background is some standard lambda CDM, but these little fluctuations are free to do whatever they want, modulo the parameterizations I've told you about. The tinier contours here, dark and light, are 1 and 2 sigma. For those of you that care, these are the ones where you put on some extra large scale structure constraints, in particular from redshift space distortions. This is one of the strongest ones we could find here. So this is really just looking at, I guess, how galaxies clump together and using that as a tracer of how, again, how strong gravity is, for example. So if you remember, this is a parameter that tells you about how strong the gravitational constant is here. So it's not a surprise that if you find something that's a tracer of how much stuff clumps together, like redshift space distortions, that especially squeezes in that direction here. And I can say more about, if you're interested in, about what physical effects do the give you the precise shape here, but just as a sort of reference point. Now, the one thing I do want to highlight is these constraints here on these parameters are order 1, right? Here we go like up to 2, maybe here we go up to 2. Now, what's interesting about this is effectively telling you that on cosmological scales, this is not really precision cosmology yet, right? This is basically telling you that our measurements of the gravitational constant on cosmological scales with purely cosmological data has an order 1 uncertainty compared to the measurement we have on Earth, right? This is not percent level or something, could be twice as big, half as big, things like this. So that's the main thing I wanted to get away from this here. And secondly, again, probably unreadable at the bottom, forecasts for the kind of near future surveys like LSST, SKA, and so on are forecasted to improve this by roughly an order of magnitude or so. Okay? So I guess we go from order 1 to maybe 10%. So that's the, take this as a sort of snapshot of the state of the art, and then we can do better there. There's lots of other interesting ways one can also improve this. So for example, in Harrison and Kessler, right, we're doing something where you also take on forecasts of future gravitational wave data. In principle, one could put weak lensing onto this as well, and so on and so on, right? So there's different ways of shrinking these contours more, but think of this as like a rough ballpark of what cosmology just by itself will do without recourse to anything else like gravitational waves. Does that make, this is the sort of question where no one ever answers, but does that roughly make sense? Is anyone already very confused or angry at me that wants to place a call in for some work I've overseen? No. Okay, wonderful. You can still shout at me later on. No? Some curiosity at the back?
I'm just genuinely.
You're just genuinely curious. Okay, very good.
No specific.
Okay, I'm touched. So let's go to the next system here. So we've already kind of put down our anchors here and there. Now we'll talk about supermassive black holes a little bit, some intermediate system and what we can learn from that. Okay, so this is where hopefully the introduction will come in handy. So at the start, in the introduction, I was trying to kind of implant this picture in your mind where you think of this soup, of this medium of the universe that's given by the background of this new physics, the scalar, and then the gravitational wave is kind of traveling on top of that background, shining through that medium, and we learn about that. Now we're going to reverse the game. Okay? We're going to find some extremely loud source, which gives us a big gravitational wave, very large gravitational wave that goes out. Now this gravitational wave will basically work as a background. This is a very loud signal. And we're thinking of the little scalar, in this case, dark energy fluctuations that live on top of this loud gravitational wave background. So it's exactly what we did before, just the actors have kind of, main role and supporting actor have reversed. Now, let's think first of a super basic example. Let's think of some small scalar fluctuation, and what some equation of motion for this thing may look like. And so here's one example for this, right? We just have something, this would look like some sort of Klein-Gordon equation. And this thing here basically tells you about the speed with which these perturbations go out. It's called the speed of sound, for analogical reasons. And so one interesting thing about this here already is that you need to be quite careful about the signs of the different terms here. If you have an equation that looks like this one here, and this is sort of first year differential equation solving, I guess, in undergraduate, and I ask you what's the solution for this pi here, this is a nice solution because it's oscillatory, right? This is going to be causes and sines, things like this. That's great if I do perturbation theory. I told you I want this scalar field to be small on top of a background. Some oscillatory solution does lots of things, but it will stay small. If I change this sign here to a minus sign, then bad news, right? Instead of the oscillatory solution, I get some exponential solution now. And so that essentially tells me that whatever I'm doing is not going to work for very long, because this thing that is predicated to be small now suddenly grows exponentially. And whatever thing comes out of my calculation is a nice sort of mathematical exercise that probably doesn't really correspond to anything, because I need to find some different description that takes into account all these nonlinearities and so on. Now, why is that relevant? Let's think of some gravitational wave event here, where there's this loud gravitational wave. Right? And so I'm cherry picking something very specific here, following the work of these guys down here, where I just have a gravitational wave with some amplitude that travels in the z direction. I put up my coordinates so that that's the frame I'm in. I have some gravitational wave. I have my box in space, and now this wave is kind of sweeping through. Now, when I'm far away from the source, I can look at my favorite gravitational wave textbook, right? And I can find what the amplitude of the gravitational wave is at some given distance r away. And surprise, surprise, it depends on a couple of things. In particular, how far away I am, what the mass is of this particular system, and the frequency. So I guess if you like, how far I am into the inspiral. Now, this is now my background, and now I do what I promised a second ago. I look at these small scalar fluctuations on top of this background given by the gravitational wave. When I do that, I find something. Font size here is really a problem. Huh? You just have to take everything I say on trust, because you probably can't read the equations. But trust me that I get something which looks a little bit like this equation up here, except now there is some big bracket which may be difficult to read, where there is this overall term here, the speed of sound term, so the one that goes as k squared, where k is the Fourier wave number, has some overall cost term here, which I guess descends from the oscillating solution of the gravitational wave. And this modulation has an amplitude that depends on the parameters we saw a few seconds ago in this slide. It's a parameter that tells you about the strength of the gravitational waves, the strength of the coupling between the scalar and the gravitational of general relativity, and on the amplitude of the wave. Now, some of you may already say this is a problem, right? Because if this is some oscillating solution here and it has some amplitude, if this amplitude is larger than 1, whatever it is, I can change the sign of this k squared term here. And then we're back to the problem I talked about a second ago. I go from having oscillating solutions to exponential ones, and my analysis goes out of the window, because I can't just do the perturbative analysis anymore. This mode grows too quickly. So, this is the kind of the brute force version of a more subtle analysis, but hopefully gets the salient points across. Now, the obvious next thing to say is this is all fine and well. Why does this actually matter, right? For the kind of theories I have, is this something where this instability just gets sourced for some systems which maybe are not actually there in nature, right? Maybe this depends on making this parameter large here, depends on having a gravitational wave amplitude that doesn't correspond to something that we have in nature. Things like this, right? How often does this happen? Does it happen everywhere in the universe? Am I really worried about this instability? And so when you think about this a little bit, you end up with a sort of a bottom line statement like the one in the box here. But let me just quickly walk you through this. So if you think of the system that I was highlighting in the initial plot, some supermassive black hole merger, where we start having frequencies not so far from the merger of 10 to the minus 5 hertz, things like this. Actually, you can scratch the last statement. It doesn't matter how close to the merger it is. We can observe these systems at frequencies of 10 to the minus 6, 10 to the minus 5 hertz, no matter exactly when that frequency is being reached. It turns out that the gravitational wave amplitude emitted by the systems is large enough like anywhere within some sort of sphere around the source of 10 megaparsec, this instability that we're just talking about gets triggered as long as these parameters are order 0.1 or larger, in particular this sum here. So you can put this into you can sort of reverse engineer this and place it as an extra constraint on the plot that we had before. We'll do that in a second. But just one more thing I want to say, because I think it's potentially interesting here. Why have I snuck this in here, this 10 megaparsec? The idea is effectively that if I'm looking at a big enough box, or in this case sphere, then if I make it large enough and I make it larger than the homogeneity scale of the universe, then I can kind of assume that what I'm doing is fairly representative, right? So here, this system is kind of, if you like, cherry-picked in such a way that in this box, which goes beyond the standard homogeneity scale of the universe, you expect it's representative of any sphere that you can draw like this in the universe. And you can then talk to your favorite black hole population person, and they will tell you that these kind of mergers happen order 10 times within a Hubble time between redshift 0 and 1. So there's a decent number of these events that happens in some sort of representative sphere like this. Okay. So this is an answer to the question, does this happen at all? Should I care? And the answer is yes, right? These events happen, they're large enough to trigger this instability everywhere in the universe in some way, shape, or form. Good. Do I have time for mentioning a subtlety? No. There is a subtlety here where this instability doesn't progress equally fast for different scales, for different wave modes. Okay, I'm going to do a nasty thing. I'm going to say I will not talk about this now, but if you want to hear more about it, I'll say later on, just because otherwise we'll quickly run out of time for talking about the systems. You can also shout at me right now if you want to force me to talk about it now. No, okay, perfect. Indifference is the look I'm going for you. Now let's put these things together, because I promised you a sort of linear story until now. So this is what you sort of a weirdly pixelated version of what I just showed you a couple of minutes ago. This little stripe down here is what happens when you put this constraint here, right? The constraint on the parameters that says I do not want this instability onto this plot. And this looks like a line, but it actually has some width. This is just because the constraint is fairly strong. And so the not wanting this instability basically restricts you to living on this particular line. So if I incorporate that as a prior into my data analysis and now rerun things, I get whoop, this little sort of set of constraints here, and that's where my 2 sigma contours actually live in here.
Why isn't there any, I'm not sure I can see it, there isn't any bit of your remaining contour below? It looks like the pink contour does go a little bit below CM of 0. Yeah, so what happens is it's sort of preferred direct. So actually this is good. This is something that I didn't have time earlier on, and now you're buying me time to talk about. So the contour down here is provided by gradient instabilities, not for the gravitational wave system we were just talking about a second ago, but in cosmological spacetimes. So some other instability. So forget about this extra constraint for now. Imagine we're back in the example in the first couple of slides. This here, this contour is given by you not being able to go in here without developing instabilities in cosmological spacetime. And so what happens is this line here sort of intersects with a good part of space, parameter space here. And as soon as you go past the 0, 0 point, you go into gradient instabilities on cosmological spacetimes. Okay, I thought that was the boundary of the pink region, like gives you gradient instabilities, like the flat line at the bottom.
That's right. And maybe I misunderstood your question.
It looks like there should just be a tiny bit of parameter space that is within the pink region, so avoiding space-time instabilities.
So that maybe I'm still misunderstanding the question. That's this, right? This overlaps with the. Am I misunderstanding? This really feels like I'm misunderstanding your question. We have audience participation, people. So there we go.
Is there not like a tiny bit of space about the same size there?
No, there isn't. It's really just the moment you go past here, then you start having instability. So there's a sort of weird preferred directional parameter space to go away from GR for these theories. Okay, I think at least I've understood the question now, so that's good. Very good. So now you may say, this is the end of the talk, right? This is awesome. This person managed to finish in 30 minutes. And you know, isn't this a beautiful story? We went from something that had these like very wide constraints to something where now these constraints are already order 0.1 or so in this parameter. You know, we can all go home, come back in 40 years because the next generation experiments will also not constrain this more, right? Isn't this all wonderful, right? No, because otherwise I would have told you there's only one linear part and no one linear story in this talk, but now we're going to deconstruct it, of course. Good. Okay, so let's change field completely. Let's stop talking about cosmology or anything like this, and let's move to the 1930s. We are in Enrico Fermi's office in Rome, and this person is thinking about what we now know as well, let's start with neutron decay, okay? Like the example I'm showing you. So this is what more or less people were seeing at the time, right? Neutron coming in, proton and electron coming out, and what people were noticing is that this isn't quite the full story, right? Because there's some momentum missing. There needs to be some new physics. Hence, they postulated the neutrino. Right? Should hopefully be the next slide if I remember correctly. There we go. So the unraveling this black box here, then gave us what's called Fermi theory, this new theory which incorporated and postulated the neutrino. There's a fun backside story for this year, where this, I guess, won the Nobel Prize about 5 years later, but before that was rejected from Nature and other journals because it wasn't, solid enough and everything. So don't despair if your paper gets rejected from the journal, I guess, is the main story and moral here. But we have this this fantastic theory now, right? We are in this 1930s office. We now understand weak nuclear decay. We have this new neutrino. We can do lots of calculations with this theory. One of the calculations we may want to do is we may want to work out something called the scattering amplitude, which basically tells us how likely is this going to happen, right? What's the likelihood of this neutron going in and decaying in this particular way? And so you can work out the scattering amplitude, which is related to this differential cross-section here. That basically tells you, how much flux, how many of these neutrons coming in are being scattered and decay in this particular way versus the ones that just mind their own business and go through. And once you do this calculation, you can also, look at various features of this amplitude that tells you how likely this process is. In particular, you will find that there's some scaling with energy, which goes a little bit like this here, where there's some preferred scale that pops up, which is around the TeV scale. Now, depending on how you look at it, right, you may say, oh, this is cool, right? I now have some understanding of how things scale with energy, or you may be horrified, right? You may say, this is not very nice, because clearly what this is telling me, this is meant to tell me something about the probability of this process happening. If there's this scaling here, if I go to large enough energies, this thing will grow and grow and grow and grow, and it will grow into a regime where it doesn't really make sense anymore, right? If it's more than 100% chance of this decay occurring, that doesn't really make a lot of sense. So somehow something is off as we go to large energies here. And we know what's off, right? Because we don't live in the 1930s. We know that actually this is not the full story, but there's something like the W boson and other particles that mediate this weak nuclear decay. Right? And the amazing thing is the following, right? Now we're the clever ones with hindsight, because we already know this here. We know that the scale of the new physics, where this picture is not really good anymore, comes in across the mass scale of this boson, right? That's the energy where you can start running experiments in the LHC or in lead before, and you can start resolving this particle and seeing it. That scale is around 80 GeV, right? And now go back to the 1930s, you could already have known that something like this had to happen, because this is telling you that things go bananas once you reach a GeV scale, okay? So the basic message here is that the theory will tell you when, what its expiry date is. This is the maximum energy it can make sense up to. And lo and behold, is it exactly that scale? No. Is it damn close? Yes. It's within 1 order of magnitude, right? 1000 GeV is a TeV. It's within 1 order of magnitude, a little bit below this sort of magic expiry scale, where the new physics comes in. Good. So now you're thinking, why the hell is this guy going on about weak nuclear decay? It's got nothing to do with cosmology at all, right? This is why I'm going on about it. So this is something we've seen already. I can do the same with GR, right? I can take two gravitons, I can scatter them. And again, the result is not a big surprise. We find that the equivalent of this energy scale here now is the Planck scale, or if you're a sort of an obnoxious particle physicist, you may call this 10 to the 15 TeV, right? So a much larger scale. But the theory tells you that, at best, the theory is valid until there, then something new will happen. So you're not impressed, right? Because you say, of course, I know this, right? GR is valid up to the Planck scale. We already knew this, fine, you can write it like this. Why is this useful? And so this is where we finally kind of complete the loop. If you now take one of these dark energy EFTs, I guess how Anson called them earlier as well, but really just any of these scalar tense theories that I was writing down, and this doesn't really depend that much on whether it's a scalar or a vector or something like that. For a large class of these theories, not all of them, but for a large class of these theories, this characteristic scale is much lower than what you see here, and it's around, say, units 10 to the minus 12 electron volts. Good. So there's lots of responses that may have to this here, but there's two very obvious ones. Obvious response number one is not so cool. Not so cool because this is a damn low energy scale, right? So you may say this is a bit disappointing because I was hoping that my dark energy theory was going to be as good as GR, right? It was going to be predictive and really give me nice predictions all the way to this 10 to the 15 TeV scale, not even close, right? This is not as good as much. Or you may say, well, what is your problem? This thing is a very low energy scale, but the scales that we probe on cosmological distance scales, they are around 10 to the minus 33 electron volts, so around 20 orders of magnitude even smaller. So you already, someone tailor-made this theory for you, which describes physics on 20 orders of magnitude. You should go home and be happy. You just your standards are too high. You're hoping for the Planck mass here, but this is still a good effective description on physics on a lot of stuff. Okay. And you are free to go either of these routes, right? Both of these are consistent responses here. Now, how are we doing now? We're getting close to the time where you will start shouting at me. No? Yeah. Okay. Good. Okay. Fine. So let me say this quickly, and then we'll transition to the final point. So now, remember the scale here at the end of the day. I've added this extra, this extra row here with the different energies. This energy scale, the 10 to the minus 12 electron volts, sits right here. Boom. In the LIGO band, corresponds to around 200 odd or so hertz in terms of that scale. So alarm bells ringing, right? If I now do what I did in the first part of the talk, and I go, isn't this wonderful? I have some constraint from LIGO. I'm just going to wedge it together with my cosmological data constraints. Right? A little bit dangerous, because we just said, when we saw in the previous examples, what happens generically as you get close to this scale here, your theory starts breaking down and some new physics, some new decompletion in the particle language starts coming in. Okay? So just taking measurements and constraints from scales here and applying them to a theory that's really valid, hopefully with something like this range, is a very dangerous exercise, right? And so that's something I really want to drive home, because before COVID, it was all in person, now it's more online. Lots of us go to lots of conferences, and I often hear a statement along the following lines. Here is this constraint from LIGO, right? There may be something funky that happens around this scale here, but we are going to be conservative and just assume that we can map this constraint over to the cosmological side here. That's not conservative, right? This is the radical option. This is saying I'm going to make fairly strong assumptions about whatever new physics comes in here, and I assume that it's such that I can safely do this thing. Right? That's a consistent thing to say, right? That's a caveat you have to your statement, and then you say that's our assumption. Our assumption will be tested in the future by things like the paper you guys talked about earlier on in the LISA van. But it's not conservative, right? This is making a strong assumption about whatever new physics comes in here. So in that sense, I guess it's very interesting to think about constraints and how much we can push them, which are inside this band, either within LISA, extra cosmological ones, and so on. good. And we already heard Claudia and Scott. We're looking into this for a while. Let me skip this equation here. Let me maybe just super briefly advertise this thing here. This is with by now postdocs, Luca Santoni, Leonardo Trombetta, and Samuel Sanghisa, and Enrico Trincherini, where we were playing with another situation here. So this is sort of disappointing having this scale here for many reasons. One of the ones is that the black hole mergers and the ring down and so on in LIGO tends to happen even further to the right here, right, on the side here. And so you would love to use this to learn more about dark energy and things like this, but even worse now, right? Now we're really into the bad part of the graph here. And so that's true for most kinds of interactions. This is why this equation is here. These guys with lots of derivatives and lots of scalar fields, if they are relevant for cosmology, this is kind of what enforces this scale here. So maybe I should say very quickly, because this also relates to a question filled out earlier in the journal club. This scale in principle can be wherever it wants, right? I can move this left, right, any side I want. The reason it sits right here is because I mandate that this new degree of freedom has something to do with dark energy, with expansion of the universe, right? That sets what this scale has to be. I can make this suppression scale here larger. That's consistent. That will do two things. That it will move things to the right, this line. So I will be able to probe this theory with other LIGO observations, but it will also suppress the impact of all of these terms for cosmology beyond where they have any real effect. So there is a game you can play where some of these new scalar physics that's not to do with these higher derivative interactions still affects dark energy over here. You raise this scale to kind of also test things with LIGO. And then you can play this combined game where now suddenly you can use LIGO black holes to also learn about dark energy indirectly. But well, as I'm probably getting across here, that's a story that takes a little bit of engineering, right? This doesn't naturally come out from this theory. Okay, so in the, I guess, final 5 minutes or so, let's try and keep it to 5 minutes and do shout at me if I go over that. No. So is the following. So you may think I've now told you this story here, and this has kind of exhausted the game, right? Because clearly now we're at this point here where to the right we need to know something about some new high energy physics, some UV completion. We don't know what that is for any of those theories. So why even look into anything over on this side here? And I guess what I want to convince you of is that even without really knowing what this UV physics is here, we can still learn something interesting all the way to the physics of cosmologies by thinking about the high energies here. And I guess the fundamental picture I want you to have in mind is the following. Imagine your assumptions about this UV physics being a sort of dial, right? I can dial this all the way up, and I can say, well, I really know that the UV physics is a specific string theory with these coupling constants and so on, right? I don't, but if you are making that assumption, then that will tell you something fairly strong about the physics here, and you can work out what the low energy phenomenology is from those assumptions. So that cranking this dial all the way up is something that gives you lots of information also about the physics of low energy. Problem with that approach is we don't know, right? This is not something that we know. But, and this is, I guess, where I'm going, I guess that what I'm going to try to convince you is that even when I dial this dial down all the way to the left, I guess, if I dial it down, and I have it as a fairly minimal setting where I'm saying, well, all I require of the physics of these high energies is that it's consistent with the most super basic principles that all the field theories that we normally write down have, and in particular that some notion of causality, some notion of locality, and some notion of unitarity, so probabilities being conserved. With this sort of low dial setting here, if we are making that assumption, we can say something interesting about the low energy physics overall here. And this is sort of like a street that goes both ways, right? So you can treat this as making these assumptions here and using them as priors for your low energy physics, or you can figure out that, if these kind of assumptions here tell you that low energy physics needs to be in some region of parameter space, then doing that low energy physics test, if it tells you that you live in a different region of parameter space, that's also a test of the UV properties of this theory, because then you know that it can't have come from something that's local, causal, and unitary. So you can pick the favorite direction of the arrow that you would like. Okay, so this is the world of positivity bounds. Scott, I think, already talked to you about something on the inflation side about a year ago. So I think we've hopefully coordinated well in terms of not having too much overlapping topics. And the basic idea is what I just told you, right? Just having these fundamental properties and seeing how they map down onto constraints on your parameter spaces on your physics. Okay, so again, right, the fundamental object here is this scattering amplitude for some process. So, you choose and tell me what the incoming particles are. Normally, the easiest calculation that is informative is some 2 to 2 scattering. Say I take this new scalar degree of freedom and another scalar, and I bounce them off each other. I can compute what the scattering amplitude, the likelihood for that process is. Or maybe you tell me, no, I want some other permutation. I want the scalar and a photon, or 2 photons, or whatever, right? So there's lots of combinations, lots of scattering amplitudes I can work out. These scattering amplitudes know about all the physics, right? All the coupling constants in your theory will sort of trickle down into the scattering amplitude, will tell you about these processes. And one informative thing I can do is I can effectively, it's a good way to think about it, I guess, expand the scattering amplitude as a Taylor series in powers of the momenta. And so this is just cherry picking one specific term here, which is some superposition of these incoming momenta for pedagogical reasons, but in principle, this is a series that goes on, right? You can expand this in terms of momenta. And then when you expand in terms of momenta, there are going to be coefficients for these different terms in momenta. This is where all the physics lives, right? These coefficients are going to be some combination of all the coupling constants in your theory. If you can say something interesting about these coefficients, you say something interesting about the coupling constants in the theory, and hence you learn something about the physics. Okay, and so this is my one-line summary of positivity bounds, completely inadequate, but again, if you want to know more, I'm happy to tell you more later on. So one game you can play here is you can say, I remember my complex analysis course from my undergraduate. I know how, what kind of contour integral I can write down that isolates this coefficient here. So right, this is what this coefficient is here. And now I have some contour integral like this here. I can work out what that is in the low energy theory. Right? I've given you some covariant theory like the scalar tensor theory, the Lewandowski theory we had before. I can work out what the scattering amplitude is. That relates to some of the parameters in the theory. But as it turns out, I can also massage this in a different way. I can make the contour larger and larger, which corresponds to evaluating this amplitude at larger and larger energies. And I can go to larger and larger energies, going past this cutoff, going into dangerous land, where I don't really know what the theory is anymore. But it turns out that by using these unitarity, locality, and causality properties and what they imply for the mathematical structure of this amplitude here, I can massage these things in such a way that I get an expression like this here for this example, which is just an integral over the scattering cross section for this process divided by some positive power of the momentum. You don't know what this is, but you do know that it's a positive number. Right? This is a positive definite thing that you're just summing over in this integral. So you have learned that this parameter here has to be positive, hence the name, right? And there's a similar game you can play for other coefficients. And so now you have these, I'm getting shouted at, okay, very good. Now you have this particular way here of learning something about different coefficients in your low energy theory, right? This is the parameter you could work out in your favorite theory, like the Lewandowski theory, and having some extra information about these parameters from these assumptions up there that they need to be sign definite, right? I can write it so that they're positive. Okay, final bit. I just want to put things together, which is essentially now saying, let's put all of this together. Let's use these as priors and also add them to the data analysis. This is the same kind of plot I showed you before, except I've switched out one of the axes. Here we still have this parameter that tells you about the interaction of the graviton and the dark energy scalar. This one here now tells you about the speed of gravitational waves. So I've ditched the LIGO constraint as advertised, right? So I'm just leaving this as a free parameter. Things are parameterized such that down here at this line, the speed of gravitational waves will be 0. Here is the speed of light and so on. So that's the normalization of these things. Now, now this is again how the contours would look like from just the CMB and large scale structure constraints on this panel in my massive triangle plot. If I now place I should really go too forward. If I now place the constraint from looking at this 2 to 2 scattering from having this new scalar degree of freedom and matter, say a photon, and I scatter them off each other, the positivity constraint I get from that gets mapped onto this as telling me that actually the gravitational wave needs to be superluminal, needs to travel faster than light. So I actually need to live in this upper part of the diagram here. Okay. So we can talk about this later on. This is interesting, right? So there's a notion here where superluminality is not quite what you expected, and actually the amazing thing here is people always have this sort of knee-jerk reaction where superluminality is not good for causality. These constraints come from causality, right? Causality actually requires you in this case that the gravitational wave needs to travel faster than your photon. So that's interesting. We can talk about it more later on. Otherwise, Rachel will kill me. So let's try not to go there. So very quickly, while I'm going through there, you can now compute different scattering amplitudes. For example, two scalars instead of a scalar and a photon. Boom, right? So now we need to be in the top left corner. So it's sort of shrunken and moved our contours even more yet again. And that's really the final point, I guess, given time, I think I want to stop on here. So what are the key things here? Number one, you didn't know whether these constraints are useful, but they tell you something interesting about the space. If now in the future, for the specific theories we're looking at here, data tells you that you really live down here, you've learned something interesting, right? You've learned that whatever the high energy theory is, it's not unitary, local, and causal in the way that certainly we would parse it now. Or you can put it the other way around, right? And you can say, well, this is a pretty good prior, right? These kind of constraints, if we really believe in them, do shrink our parameter space a lot. And so they are useful, right? So there's some notion here of identifying what the physical and the unphysical parameter spaces are. Okay. Let me just say one sentence for the bottom thing here. So here we've the scattering is something that happens really in the realm of particle physics. So on flat Minkowski style backgrounds, sometimes that's a problematic assumption for cosmological theories. This is true for some kinds of theories, but it won't be for others. And so trying to compute these kind of bounds on space-times, which are a little bit more like the cosmological ones, is kind of like an ongoing direction to make these bounds more and more and more robust. And so advertisement, right? Like if you want to hear more about this, you can either bother me later on or have a look here. Okay, and I think I haven't done too horribly, hopefully, so I'm hoping Rachel's still okay with me. I'm going to stop. Thank you so much.
All right, well, thank you very much. I guess we do still have time for a question or two, so I'm going to start by saying, does anyone online have a question and want to speak up? I see Alex has a hand up, so feel free to just.
Yeah, my question is, if you calculate action of gravitational waves on dark energy, right? What kind of